Welcome to this presentation on diagnosing crashes and memory errors in C programs in Linux. In this presentation, I'm going to talk about how you figure out where your program crashed and perhaps a little bit about why it crashed, and also how to find out about certain kinds of memory errors, buffer overruns, memory leaks in your program. This is a presentation for beginning C programmers in Linux. C has many pitfalls, and by default, when you run a program and it crashes, you don't get any indication of what line number the program crashed on, which makes it difficult to determine what the problem was. Also, when you have problems like buffer overflows or invalid pointer dereferences, those can also be difficult to troubleshoot. So in this session, I'm going to talk about how to diagnose and troubleshoot these kinds of problems. To begin, let me show you what happens when we run a program that crashes without any special techniques. So here's a program. Here's the main function. It calls a function named crash, passes the value 0 in, and this causes a division by 0, which is illegal in C, and causes a crash on line 17. So I'm going to go ahead and compile this program and run it. And we get this floating point exception message. And there's no particular indication of what line caused the problem. The first thing I'm going to show you is how to use a tool called Valgrind, which is a tool that helps troubleshoot runtime crashes and memory errors in C programs. And you can use this in Linux and Mac OS, and also the Windows subsystem for Linux. Using Valgrind is pretty easy. If you run a program that has command line arguments like this, /myprog, and then pass the command line arguments without Valgrind, to run the same program with Valgrind, you just put the Valgrind command at the beginning and then run the program with the same arguments. So I'm going to do that. I'm going to run crash with Valgrind using this command right here. So over here, I type valgrind./crash and press enter. And we get a bunch of output from Valgrind. But in particular, when the program crashes, you see this message right here, and it tells you that it crashed in the crash function. Now, it doesn't give you any line numbers. I'll show you how to get line numbers in just a moment, and it shows you that crash was called from the main function. So even without line numbers, this at least helps you zero into the portion of your program where there was trouble, and you can do some additional diagnostic work at that point. To get additional information about the line numbers, you want to use the -g command when you compile your program. So I'm compiling crash.c with the -g switch and creating an executable named crash, and I'm going to run it now with Valgrind. And now we actually get line numbers. So it shows you that main on line 22 called crash, and then crash died at line 17 with the integer divide by 0. So it pinpointed the exact line 17, where the crash occurred. Now, what about all of that Valgrind output? Well, when Valgrind runs a program, it writes diagnostic information to what's called the standard error stream, in lines that are prefixed with the process identifier with little equal signs around it. So over here in the output, you see most of the lines that are being output here are coming from the Valgrind troubleshooter. It's showing you that it's starting up here, and it's showing you the command that it's executing. This is the one line of the program right here that didn't come from Valgrind. That came from this line right here, this command in the program that printed out the message, prepare to die. Now, if it confuses you to see your program's output, that your program's output doesn't have the PID in front of it, you can redirect Valgrind's output to a separate file using this technique. So I'm going to come over here and type valgrind /crash, and I'm going to have it redirect with the 2 greater than. This is the part of the command line that tells bash to send the standard error stream to a file, valgrind output.txt. And now the program's regular output appears on the screen, and if you want to look at the valgrind output, then you can use the cat command, cat valgrind output, and that displays all of the valgrind output. So that may help you to keep those 2 bits of output separate. Now, in addition to using valgrind to determine where the program died, you can actually use additional compiler options. And these 2 that I've highlighted here can be used to include additional runtime checks, so that when the program crashes, you can get that helpful crash stack trace without having to run the program with Valgrind. And you put those additional options right onto the compile command. So in our case, I can come over here and type gcc. You want to use -g so you get the additional line number information. Add the f no emit frame pointer option, and then we're going to compile crash.c and produce crash executable. And now when I run it with crash and the program dies, you see this crash error message, and you see again line 17 is the line that created the issue. So the program just runs normally. You don't get all of the same amount of additional diagnostic output that Valgrind gives you, and this may be preferable to you. Now, when you compile the program that way, you cannot use Valgrind with it. Those flags produce programs that are incompatible with Valgrind, so you can use either the compiler flags or just compile without the compiler flags and use Valgrind. These are 2 techniques to help you figure out why your program died. One additional technique I want to show you is how to get a core dump. You can configure Linux to create a core dump when your program crashes. A core dump is a file named core that contains a snapshot of the memory of your process at the time that it crashed, and you can use this to inspect the variables and find out the contents of memory at the time that your program crashed. To configure Linux to create a core dump, you use this command in your shell, ulimit-c unlimited. So I'm going to go ahead and demonstrate that. ulimit-c unlimited. Normally, the default behavior for many modern, well, at least Ubuntu, this particular recent version of Ubuntu I'm using, is to not create core files. The unlimited, the -c unlimited tells it that it's allowed to create a core file of any size, and you could specify a limit on the core dump size if you were concerned about the size of the file that it might create. And now we're going to run the program, crash, and it crashed. And we have now a file. Actually, it didn't. It looks like it. I'm sorry, it didn't dump core. Let me go ahead and recompile it with standard switches. So crash.c, and I'm going to run it again. And there we got core dumped. So those flags that I showed you earlier that are incompatible with Valgrind will also prevent the creation of a core file. Now, once you have your core file, you can use a utility called GDB, which is a debugger tool to inspect the core dump with a command like this. You type GDB and then the name of the executable that crashed and then the core file. So GDB, the name of the executable was crash, and our core file is core. You can see it's a fairly large file. It contains the complete memory image of the crash process at the time that it died. And when you start GDB, you get a bunch of output like this, followed by these messages here. Program terminated with an arithmetic exception. It tells you what line it crashed on, line 17. It's showing you the contents of a key variable in the expression. Num had the value 0, and then it's showing you the full line. Now there's a couple of GDB commands that you can use here. One is the command list. This shows you that line in its context. This was line 17, so there's the line. You can display the values of program variables using the p or print command. You can type print num to get the value of that variable at the time of the crash. And you can also find out what the stack trace was by using the bt command for backtrace. Shows you that crash was executing on line 17, and it was called from main on line 22. And if you want to see what the values are in main, you can type list main, and this shows lines in main. And if you want to navigate up to the main function, you can type the word up, which allows you to inspect the values of variables in the main function. Sometimes it's useful to see what the values of the variables were in the function that called the function that died. So we can type print argc to see the value of the argc variable and other commands. I'm not going to go into a full discussion of the commands, the GDB, the usage of GDB. That's a subject for a separate video. When you're finished inspecting the variables, you can just type quit, and that will get you out of GDB. Now I want to talk about diagnosing memory errors. Valgrind, in addition to giving you helpful information about program crashes, can also help you troubleshoot memory leaks and buffer overflows. And I'm going to demonstrate that with a program named Leaky. So let's take a look at Leaky. Leaky starts out by using the malloc function to allocate some memory, and then it calls a function to allocate some more memory. Here's the alloc more memory function. Alloc more memory allocates memory with malloc, and it checks to make sure that the allocation succeeded, and it fails to deallocate that memory. So we have a memory leak. Main eventually frees the buffer that it created and then returns. And I want to show you how, first of all, we can find out that our program has a memory leak, and then determine where the memory leak originated. So I'm going to go ahead and compile leaky.c, and we can run it, and there aren't going to be any error messages because a memory leak doesn't typically result in error messages. Let me go ahead and run it with Valgrind, and let's look at the output of Valgrind. So the program ran, there was no output from the program. At the end, in this heap summary, there's this message: in use at exit 256 bytes in 1 blocks. And in the leak summary, it says definitely lost 256 bytes. That is a direct reference to the fact that we allocated this 256 byte chunk of memory, but we failed to deallocate it. There weren't any program variables that could have referenced it at the time the program exited, and so that memory was leaked. There's this additional message here that says rerun with leak check equals full to see the details of leaked memory. So I'm going to do that. Valgrind leak check equals full with our leaky program. And now we get some additional information. So in the heap summary, in use at exit 256 bytes, it says 256 bytes are definitely lost, and it tells us where in the program that memory was allocated. It says it was allocated by the call to malloc that occurred in alloc-more memory on line 14. That's pointing us to line 14 right here. That message is saying, hey, that line allocated some memory, and nowhere in the program was that memory deallocated. So that helps us to troubleshoot the fact that some memory was leaked. Let's look at one other example. Let's look at overrun.c. Overrun.c takes a command line argument and passes it to the function overrun. Overrun, in turn, takes the string that is given to it and copies it to the buffer named buff, which is large enough to hold a 5-character string plus its null terminator. Now, when you run this program and you supply an argument on the command line that's up to 5 characters, there's no problem. But if it's 6 characters or longer, then we're trying to put data into a variable that's only large enough to hold a 5-character string, and that can cause problems. Let me demonstrate this. I'm going to go ahead and compile overrun.c, and I'm going to run it and give it the command line argument that it needs, and I'm going to give it a 6-character string. And that was too large for that buffer to hold, and it doesn't appear that that caused any particular problem. But that is that is just an indication that the problem was not surfaced. If we type a slightly larger string, then we do in fact get an error message, because we have now overflowed the buffer enough that the built-in buffer overflow detection that the compiler includes in our executable has determined that we have written more data into that local array than it is designed to hold. We can get a little bit more information about the problem if we run it with Valgrind. So let's run it with Valgrind. And here you see the error message, the process is terminating, and it gives you the stack trace. And if you look down the stack trace, the first line you come to is the line that we're interested in. It's overrun.c, line 24. Now, in this case, line 24 is the end of the function. The problem actually occurred on line 23, but the buffer overrun detection logic that the compiler uses doesn't actually analyze and check for buffer overruns until the end of the function is reached and it's preparing to return to its caller. So there's some limitations there of the technology. But still, we get an indication of where in the program we have an overrun. That concludes this presentation. Thank you for watching.